Now we're going to talk about finding the mean from a frequency distribution. So in a case like this, the place you would use this is if you weren't given all of the raw data values, if you didn't have all the data values just laid out for you and instead you were given them in a frequency distribution, this is when you would need this. So we have here a frequency distribution that gives the weight of a sample of 100 babies born at a local hospital. So understand that just this part here is the frequency distribution. There's a couple extra columns just to help us, but they're not really needed unless you find that it's helpful. So in this frequency distribution, you have the weight of the babies and then how many of the babies weighed those weights in that range, that class. So for example, you got your little preemie babies here, and there's 5 babies that were between 3 and 4.9. So maybe you have a baby that was 3.1 pounds, a baby that was 3.7, no need to write this down, a baby that was 4 pounds, a baby that was 4.2 pounds, and then say another baby that was 4.2 pounds. So say that those are the 5 babies. Point is, you don't know. You don't know what the actual weights are. So when we find this mean, we're really kind of doing an estimate here of what the mean baby weight was for these 100 babies. So the way that we do that is we find the class midpoint for each class. So this takes you back into chapter 2, but the class midpoint is found by doing the lower class plus the upper class and dividing by 2. So lower class limit plus upper class limit. And if you do that, you get 3.95. And that's in the middle of 3 and 4.9. So 3.95 pounds is the midpoint of that class. So what you can do, if you'd like, is pause and see if you can get the other 4 class midpoints. What you should see is that you'll start seeing a pattern happening. And there we are. So there's all our class midpoints. And then this column tells you to multiply the frequency, how many values are in that class, times the class midpoint, which we just called X. Because the mean of a frequency distribution is right here. Notice it's a sample mean if you have a sample, which we do. And it says, find this thing, which is what we're going to find right here, and divide it by how many data values you have, which is actually going to be, is actually going to be right here. So we're just finding those 2 in the columns. So first off, before I do my last column, the frequencies is just how many babies. And we already know we can add those values up, but we already know by the information that we have 100 babies. So this column, the last one we need, is taking the frequency and multiplying it by the class midpoint. So 5 times 3.95, that is 19.75. And then the next one, 32 times 5.95. So you're basically just trying to find out what is the total weight of the babies in that class by doing the estimate of the class midpoint by times how many. So if you want, go ahead and find the other 3 values, and you can pause while you do that. And at the bottom there, you want to sum all those. So remember that that sigma is saying, now add all those values together. That is what sigma is. It's a sum. You do that, you get 767. So finding the sample mean just says take this value, which is essentially, that's pounds. That's saying here's basically all the pounds of the babies, which is adding them all together, and dividing by how many babies there are. So there is a complete relationship with what the mean is. And then because our round off rule is one more than the data set, we are actually, now that I think about it, we're actually okay, because by looking at the weight, it looks like they were probably given the weight in 1 decimal place to 1 decimal place. And so rounding to 2 decimal places is perfect. So this is pounds. So we're really saying the average or mean baby weight from this frequency distribution is 7.67 pounds. And that makes sense because if you look at the frequencies, the most frequencies are happening here, 32 and 40. So it makes sense. And then of course, you know, you've got your 18 over here, which isn't quite as many, but there's some there. So it's kind of like, it's not surprising that it's weighting it towards where the highest frequencies are. So the 7.67 sits in this class. And again, that's not surprising. You can see that this kind of has a normal distribution. The frequency is 5, then 32, then 40, then 18, then 5. So the mean sits approximately in the middle. Okay, moving on. Resistance statistics. Some measures of center are more resistant to outliers than others. So this idea of resistant, we're going to look at an example. We have some wait times at a dentist's office. All right, so you've got some people that waited, a couple people that waited 1 minute, 2 minutes, 3 minutes, 5 minutes. Find the mean and median. So if you want, you know how to do this, pause it, see if you can find the mean and the median. Four, 5, 6, 7, 8, 9, 14 divided by 6. So that gives us about 2.3. So 2.3 minutes is the mean. I'm going to round that to 1 decimal place because my numbers, my data values are whole numbers. And then for B, the median, they're already in order. So really, because I have 6 values, it's 2 plus 2 divided by 2, which gives us 2. So the median is 2 minutes. So those are a couple measures of center there. Now, what if for some reason the dentist got into a ton of traffic and could not be there and somebody had to wait 102 minutes? So now we have this really huge, big outlier data value in our data set. So let's find the mean. Again, you can pause and find the mean and median if you want. I'm just going to take the data values that I already know I have 14 for the others, and then I'm going to add the 102, but now I have 7 data values, and so that's going to give me about 16.6 minutes. And then my median, I've got now 7 data values, so it's going to be the 4th data value. Okay, so the big thing here is the measure that is resistant to the added value is asking which of the value changed the most and which didn't change. You can see that the sample mean, whew, that changed. That went from 2.3 minutes, the average amount of time that somebody waited, to 16 minutes. That's a ton. As far as the median goes, it actually stayed the same. So notice it did not change very much, and that's because the median is resistant. Because it's in the middle, it's just the middle value. It's not that odd for it to be very, very similar whether you have outliers or not. So sometimes that can be a big help. All right, moving on. So we have a couple different histograms here. When data is skewed, that means that there's extreme values in the tail of the distribution. And when you have that, like some really, like we just saw, some really, really large value, or possibly a really, really, really small value, it pulls the mean in the direction of the tail. So as you noticed, we had a data value that was 102 minutes, and that took the mean of 2.3 and made it into 16.6 when, of course, we had it added. And so the mean now got bigger. So it tended towards that really extreme value of 102. So what that means is when you have data that's symmetric, what's really nice is that you'll find that the mean and the median are approximately the same. They might not be the exact same number, but they're close. And another little tip for you is that the mode is also the same place, because you can see that the highest value there is right in the middle. Okay. Now, really quickly, I'll give you your random piece of information for the video quiz, which is that the necklace I'm wearing right now was given to me by one of my best friends when we were friends. We had been friends for 20 years, so that's how old I am. So just remember, I'm wearing a necklace from one of my best friends for 20 years of friendship. Okay, finishing this up, skewed left. So when we have values that are skewed left, what that means is you're going to have some values that are very, very small. That's in the tail, right? So there's small values and they're a very low frequency. So the mean is pulled towards that. So your mean's going to be over here, and that means it's going to be less than your median. And then the opposite happens when you're skewed right. So you might have some very, very large values. They're a low frequency, but because they are large, they're going to pull your mean towards the direction of the tail, and your median is then going to be smaller. So you might have your mean sitting here, and your median might be, say, here. So they're just different data values. And then again, mean might be here and say median's here. It really just depends on your data set. But what we really like is when we have that symmetric data and the mean and the median are in the same place. Okay, so if the data are symmetric, we would typically use the mean as the best measure of center, the thing that we would say, here is the middle of the data set. But if the data is skewed, you may find that the median is actually a better measure of center. That is not uncommon. Now, FICO scores, those are our scores. Those are essentially credit scores, which every adult has. Some of you probably know your credit score, some of you don't. Typically, they range from 300 to 850. So you can't actually get, you can't get a 0. So a higher score indicates that you have more good credit. And the distribution of FICO scores is skewed left. So you can look back up at the top of the page to see what skewed left looks like. And that's because a lot of people have very good scores and very few people have really, really horrible scores. The median score is 723. A couple questions here. If you want to pause and take a moment and think about what the answers would be to these, that would be great. So do you think the mean FICO score is greater than, less than, or equal to 723? We take a look at our skewed left and we see that when we have a skewed left data set, we know that the mean is less than the median. So that tells us that we think mean FICO is less than 723. And proportion of individuals who have a FICO score above 723, you might say, how would I know that? But the key thing here is the median. The median is literally in the middle. So because the median is in the middle, you have half the scores below and half the scores above. That's just always true. That's what the median is. Half the scores will be below, half the scores will be above. So if 723 is the median, half the scores are above 723. Okay, that is not a guarantee with the mean, but that is a guarantee with the median. And then the last thing in section 3.1, we'll be thinking about what we just talked about. We have 4 data sets where we're given the mean, median, and that's it. And your job is to try to match A, B, C, and D with which of the 1, 2, 3, or 4 fits based on the shape of the graph. So just underneath, put 1, 2, 3, 4. Take a look at these and think about which values. Pause, try it, and then come back and we'll take a look. So the answers here, notice that we have a bell shape here and a bell shaped here, but this D is the most bell shaped. I would definitely call that like looks pretty good. It's coming up, it's coming back down. So because of that, it's going to have its mean and median be the same. Now, and again, it could be a little bit different, but in this case, with what we're given, they're the same. For this one, for A, they look very, very similar, but A isn't quite as normal. So it's going to have a slightly different mean and median, but they're going to be very close. So because of that, this is 4. 31 and 32, the mean and the median. And that kind of fits because you know it should be somewhere here, which would be 25 and 35, whereas for 1, it makes sense that it's between 38 and 50. So that can help you too. Here we have a skewed right. So you can look at your notes. Skewed right is going to tell us that our mean should be greater than our median. So that's going to be number 3 for a mean that's greater than the median. For C, that leaves us with what's left, which is that it's number 2. However, understand that because it's more skewed left, what we have is that you can look at your notes. The mean should be less than the median because you're pulling the mean in the direction of the tail, and that's why it's number 2. So that is section 3.1.